Start.
Yeah, okay. Okay, so my screen is visible, right? Okay, sure. So welcome to IIT and Gate classes. So today we will be discussing about jet propulsion part of Gate Aerospace 2013 paper. So myself Akshay. So in 2013, there were total 8 questions they are asked based on jet propulsion part. So out of which like 5 were 1 mark question and 2 were 3 marks question, totaling about 11 marks. So that 3 mark question, one of which is linked question type, so which is no longer a gate pattern, but still that carries 2 mark questions. So let us jump on to the session. Okay, the first question is, consider 2 engines P and Q. In P, the high pressure turbine blades are cooled with a bleed of 5% from the compressor after the compression process, and in Q, the turbine blades are not cooled. Comparing engine P with the engine Q, which one of the following is not true? So the keywords we have to see here is, the first keyword you have to able to recognize is they're asking not true. It's not the true statement they're asking. Which of these are false? That is what they're asking. Okay, that's important keyword we have to know. Now we will try to analyze this problem. So we have 2 engines. Say like I have engine P and then I have engine Q. Okay, so I have a compressor unit over here, and then I have a turbine unit. So in between I have a combustion chamber. Okay, similarly for the engine Q also, compressor unit and then the turbine unit. So now we will try to analyze this problem systematically. So what is happening in engine P, we have a flexibility such that some of the airs at the exit of the compressor is fed to a turbine blade for the cooling purpose. In engine Q, we are not doing so. So now the major assumption I am going to make here is, because in the question it is not clear, so I am going to make an assumption over here to go forward to answer this question, is that compressor is working in similar condition, both the cases P and Q. So my compressor performance is not changed due to the bleed. Okay, so that is the assumption I am going to make, so that whatever is upstream to the combustion chamber, it is not going to change. Okay, performance wise, though there is a mass flow rate which is coming into the combustion chamber, which will be reduced compared to this one because of the bleed air, but we are neglecting that part because this will be very less compared to the overall mass flow rate which is coming into the combustion chamber. So that is the assumption we are going to make here. So now you see here, so what is the purpose of cooling, right? So the purpose of cooling is to make sure the direct heat transfer from the hot gas to the turbine blade is to reduce. So to reduce the direct heat transfer, so we are doing the cooling purpose. What's happened? So let us try to treat this problem in a bit different way. Say like I have a flat plate, right? So I have a free stream which is coming with some velocity u infinity, right? So what happens? So there is a flow, and say this hot plate is heated or something like that. So what happens when I blow the air or some fluid? So what happens? There will be a naturally the flow will take out some heat from the plate. That means like there will be a heat transfer given by it is temperature of the fluid and temperature of the plate. So depending on TP minus TF, so there will be a heat transfer, right? So because of that one, there will be a natural heat transfer. So this is the same scenario now happening here. I have a very hot gas which is coming out of the combustion chamber, and turbine blades are exposed to that particular air stream. So, or gas stream. So there will be a heat transfer from the hot fluid to the turbine blade. So that will rise the temperature in the material or the thermal stresses. That means like there is a limitation to that temperature of the gas which is coming onto the turbine part. Now, since we are able to cool the air to some extent, that means now what happens? So treat this flat plate to be a part of a turbine blade. So now what happens? There is a bleed air which is coming in like this. Okay, so let me just use the different color so that it makes much more clear. Okay, so there is a bleed air which is coming onto the flat plate from the bottom. So now what happens? There is a cool air, some layer of cool air. Above that, I have a hot stream. Above that, I have a hot stream. So now what happens? Instead of the heat transfer is taking place from hot fluid to the plate directly, now it sees a region of cool air. So that means there is a heat transfer to this colder fluid, then that heat transfer is going towards the plate. So that means there is a reduction in heat transfer directly to the plate because of the existence of the cold air, right? So that is why what we can do now is like we can increase the incoming fluid temperature little bit higher than what we had, like TF is what we had initially. So now I can go to TF2 which is higher than TF1. So say like that. So because of that, I can increase the incoming gas temperature. So this is the physics we can deal with now. Right now I can play with, since I have a cooling mechanism incorporated to engine P. So if I do this, what are the variables which is going to be affected? That are given as an option here. One is turbine inlet temperature is higher for engine P. We can write, because we are cooling now, I can increase the turbine inlet temperature, right? So this option is true. So then specific thrust is higher for engine P. Obvious, right? Because specific thrust is dependent on, so say thrust is dependent on exhaust is proportional to exit velocity, right? I can increase the exit velocity because my temperature at the turbine inlet is increased. So that implies temperature at the nozzle inlet is also going to increase. So that means I am going to expand from T04 to some exit temperature TE. So that increases my exit velocity, exhaust velocity, that indeed increases the thrust or the specific thrust. So this is true. Then compressor work is same for both P and Q. That is an assumption we are going to take because upstream we are not changing anything. So this is also true. Fuel flow rate is lower for engine P. This is very interesting part we have to analyze. So see here, I have certain temperature T02 over here and T03 over here. So similarly, in this case also T02 to T03 I am increasing. So I will call it as T03 dash, that is the engine P, T03 is engine Q. Since I can increase T03 dash, that means like I can increase the fluid temperature to higher value. How I can increase? Because if I use the energy balance in the combustion chamber, that is H03 to be equal to H02 plus energy added. Energy added is nothing but m dot F times calorific value of the fuel. So I am not changing the fuel. But if I want to increase this part, total enthalpy at the exit of the combustion chamber, indeed temperature at the exit of the combustion chamber, if H02 is not changing, that is T02 is not changing. So how am I going to increase? For the same fuel, QCV is fixed. The only way I can increase this T03 is by increasing the mass flow rate of the fuel. That's the only option I have. So that means for engine P, the fuel flow rate is more than the engine Q. That is actually wrong statement. So they are given fuel flow rate is lower for engine P. That is wrong, right? So this is actually a false statement. So out of this, the not true condition is option D. Everybody clear? Yes. So it was very interesting question. So let us move on to the next one. The mass flow rate of the air through an aircraft engine is 10 kgs per second. The compressor outlet temperature is 400 Kelvin and the turbine inlet temperature is 1800 Kelvin. The heating value of the fuel is 42 megajoules per kg and the specific heat at constant pressure is 1 kilojoules per kg Kelvin. The mass flow rate of the fuel in kgs per second is approximately. Again, it's an extended version of the previous problem. So what we can do is, the best way to approach this kind of problem is first draw the control volume and get all the variables cleared out. So I have a combustion chamber. Okay. So I have few inlet conditions. I have a air which is coming in m dot A with a temperature T02 and I have an exhaust condition from the combustion chamber, that is m dot gas, which is equal to m dot A plus m dot F. That means I'm adding some amount of fuel to the system. So now the exit temperature is T03. So they are given in an indirect way. The T02 is nothing but the compressor exit temperature. That is what they are given, 400 Kelvin. T03 is nothing but the turbine entry temperature. So that is also given, 1800 Kelvin. Then the heating value of the fuel added. So I'm adding some fuel which has a heating value or lower heating value, that is 42 megajoules per kg of fuel, right? So that is the energy content in the fuel. So now I have mass flow rate of air which is coming in, that is 10 kgs per second. So now what they're asking is, to balance the system, what amount of fuel am I actually using? So that is the question they are asking, and they are asking you to treat Cp for both air and gas as 1000 joules per kg Kelvin. So this is given. Okay, so now again we are going to do the energy balance. Go to next page. Yeah. So if I do the energy balance, that is the total enthalpy at the exit of the combustion chamber is equal to the total enthalpy of the incoming airstream plus the energy whatever we are adding as a heat energy. So that is combustion chamber efficiency times the QCV. This is the energy content within the fuel times amount of fuel you are adding. So that makes out the total energy you are adding to the system. So now you see, so sorry, this is H02, right? So if I write H to be mass flow rate of gas times Cp of gas times T03, which is equal to mass flow rate of air times Cp of air times T02 plus m dot of F times combustion efficiency times the lower heating value of the fuel, right? So now I can write m dot of G, that is mass flow rate of gas, using the continuity as mass flow rate of air times plus mass flow rate of fuel times CPG T03, which is equal to mass flow rate of air times Cp of air times T02 plus mass flow rate of fuel times combustion efficiency times QCV. So now if I take mass flow rate of air common, so that gives me 1 plus F, that is F is nothing but mass flow rate of fuel to mass flow rate of air, that is I am representing as fuel to air ratio, CPG times T03 equal to, if I take mass flow rate of air common here also, so that makes it to be Cp of air times T02 plus m dot F by m dot A, that is again fuel to air ratio times combustion efficiency times QCV. So from both the side I can take out mass flow rate of air. So now if I express this in terms of fuel to air ratio, F, so that comes out to be CPG of T03 minus Cp air of T02 whole divided by combustion efficiency times the heating value minus CPG of T03. Now you see everything is known to you. Cp is known. So in this question, you can treat Cp is same. So I can just take Cp divided by combustion efficiency. I can treat it as 100% since it is not explicitly given any value. So I can treat 100% efficiency of combustion minus Cp of T03. Now you keep all the numbers. If you keep all the numbers, you should get F is equal to 0.0343 something, 3483. And F is nothing but mass flow rate of fuel to mass flow rate of air. This is not we are asked to calculate. We are asked to calculate what is the mass flow rate of fuel in the question. So this is where you have to be extra careful. Okay, so mass flow rate of fuel is nothing but F times mass flow rate of air, and mass flow rate of air is given in the problem, that is 10 kgs per second. If you multiply with this F, that is 0.3483 kgs per second. So you can keep like 0.3483. So you can keep it to 3-digit place if you want, or you can round off to second digit. It's also fine. Okay. So everybody clear, right, for this problem? Okay. So let us move on to the next question. Okay. For a given inlet condition, if the turbine inlet temperature is fixed, what value of compressor efficiency given below leads to lowest amount of fuel added in the combustor of a gas turbine engine? Again, very interesting question, and there is no straight way to answer this particular problem. It is more of a qualitative analysis than the quantification. So let us try to analyze this problem from two different perspectives. First, we have to understand the given problem statement very carefully. Again, it's kind of an extension to the previous two problems. So you see here, in the energy balance, just we did for the last problem, we came to a conclusion that fuel to mass flow rate of fuel to mass flow rate of air, that fuel to air ratio can be written as Cp times T03 minus T02 divided by QCV minus Cp T03, right? So this is what we saw in the last problem. So now you see here, in the given question, they are saying T03 can be fixed. That is, turbine inlet temperature is fixed. So that is the constraint they are already given to you. So now what happens? Mass flow rate of fuel to mass flow rate of air will be dependent on Cp times T03 minus T02 divided by QCV minus Cp T03. So now you see here how mass flow rate of fuel is dependent on T02. If T02 increases, m dot f decreases, right? For a given mass flow rate of air. That is the assumption we are going to take to analyze this particular equation. If I increase the T02, that means I can use a lesser fuel to get the same T03 value, right? That is clear from this particular equation, because this is constant, and this is obviously constant if I am using the same fuel. So that makes, if T02 increases, m dot f decreases. That part is clear, right? This is part one. So that means if I want to decrease the mass flow rate of fuel, that is was asked, which given below leads to the lowest amount of fuel added. So that means if I want to decrease my fuel addition, that means I have to increase the turbine exit temperature, compressor exit temperature. That is the part one of this question. So now we will see how efficiency of the compressor is related to T02. That is the next question we have to address to come to a conclusion, right? So if I look at the efficiency of the compressor, that is nothing but T02 dash minus T01 ideal work divided by actual work, right? So this is the temperature we are interested in knowing, right? So now T02 is equal to T01 plus, if I take T01 common here, that becomes T02 dash by T01, that is compressor pressure ratio to the power of gamma minus 1 by gamma minus 1 whole divided by efficiency of the compressor. So take T01 outside. So that becomes 1 plus pi c to the power of gamma minus 1 by gamma minus 1 divided by eta c. How T02 is related to compressor efficiency? Can anybody quickly say? If I increase the efficiency, what happens to T02? Decreases, right? So the question is clear now. If I want to add less fuel, what I have to do? I have to increase the T02. If I want to increase the T02, what I have to do here? So here again, I am fixing the same pressure ratio in the compressor. So that is the important key factor. And for the given inlet condition of the compressor, these variables I am not changing. So this is the constraint I have to have here. So that means if my compressor efficiency decreases, then T02 increases, right? From this particular equation, we can conclude like that, right? So now you see the options. Which of these options is now correct? Which of this option has the least compressor efficiency? Option D, right? 0.8. That's the correct answer. So since this question is being asked, okay, there is a catch we have to take from here. It's kind of a contradicts our idea, right? If compressor efficiency decreases, that increases the T02. If T02 is more, that means like I need a lesser fuel to get the same turbine inlet temperature. This kind of contradicts, right? If I use the less efficient compressor, that gives me less fuel added to the engine, right? It's a kind of contradicting idea what we have studied so far. So the catch here is very important. Okay, because in this question we fixed pressure ratio constant. This is very, very important variable to consider. So let us try to see the TS diagram. So that makes it more clear. Okay, I have TS plot for the compressor, right? So now you see I have a same compressor inlet condition P01, and I have a same pressure ratio that is going to be P02. Okay, so now I have a state 1 from which it is starting T01, right? So now this is my constant entropy line. Okay, now consider a case 1 where you are rising to T02. Just take a different colors here. So consider a condition 1. I am going to T02. That is this much of delta S change. I'll call it as delta S1. So now you see I'm fixing the same pressure ratio, but I want to increase the temperature, the exit temperature. How it looks like now? If I want to increase, what happens for the same pressure ratio? So I have to reach somewhere over here, right? Because the pressure curves on TS diagram is diverging, right? So this is my T02 sub B, I will call. This is sub A. I have this is sub B. So now what happened? Though T02 sub B is greater than T02 sub A, by doing so, what actually happened? My entropy of the system increased further. That means delta S2 is greater than delta S1. That is the indication of decreasing compressor efficiency, right? So compressor efficiency kind of quantifies how much are you are deviating from the ideal work, that is isentropic work, right? So now delta S2 is greater than delta S1. That means the irreversibilities in the system is more now. That is going to contribute towards the loss, definitely. And what else you can observe from here? What exactly it means? That means my compressor has to do a much more work compared to its ideal counterpart, right? To overcome this loss and to get the same pressure head, right? The idea of compressor is to increase the pressure, not the temperature. The temperature is coming along with that. But the idea of compressor is to raise the pressure from one state to another state, the total pressure head. And now to do the same total pressure head increase, now compressor has to do much more work. That means it has to draw more work from turbine to overcome the loss. Okay, so in a way that we are actually losing the energy, right, in the form of irreversibilities. So there is a irreversible part of the system which going towards the increase in entropy of the system, which is not desirable, right? So indeed, like, it is not like we are just adding less fuel here, we are actually losing the useful energy. That's the part we have to understand. The question does not specify that. That is just based on our math analysis we got to the conclusion. But if you go on to look this one, you cannot take a general statement out of that, right? If I use the less efficient compressor, I'm going to use the less fuel. No, it is not like that. So we are actually losing the energy also. That we have to be very careful. Okay, I hope you guys are clear with this idea. Okay. Okay, so let us move to the next question. Gas turbine engine is mounted on an aircraft which can attain a maximum altitude of 11 km from a sea level. The combustor volume of this engine is decided based on the conditions at. Come on, this is a very straightforward question. Yes, it has to be option D, right? Because you see, we design an aircraft engine based on the conditions at which it is going to operate for a maximum duration. That is the cruise condition. So if my aircraft is flying at 11 km altitude, that means my design consideration has to be coming from 11 km altitude, not from the sea level condition or the takeoff condition. Takeoff is a short duration compared to the overall flight regime, right? So it has to be designed for the given altitude where it is cruising. Okay, that's the condition we have to achieve first. So it is based on the cruise condition, 11 km altitude here. Okay then. Which one of the following shows the correct variation of stagnation temperature along the axis of an ideal ramjet engine? Come on, this one you guys can answer first. Yes, option B, right? So let us see why option B is correct. Let us consider a ramjet engine. Again, I'm drawing just a control volume. Okay, so I have a supersonic inlet, then following a combustion chamber, then I have a supersonic nozzle. Okay, so now I have a state 1, state 2, state 3, and at the exit is state 4, let us call. So this is my axis of an engine, center. So they're asking how the total temperature, I have some say, I have T0 at the entry, how it varies along the axis of a nozzle. So this is my direction through which I have to look. So Z axis, say this one, and this is my Y axis, say. Okay, so through which I have to look how it is actually varying along the z-axis. So what is intake? It's an adiabatic duct, right? It is not an isentropic for true sake because we encounter a shock wave and all, but still we can treat it as an adiabatic. So that means for an adiabatic flow in a steady condition, so for a calorically perfect gas, I can treat T naught is going to be constant. So from state 1 to state 2, T naught is constant. Clear? So from state 2 to state 3, what we are doing? We are adding an energy and no work is being done in the combustion chamber. Only thing which changes is the system energy level. That means indeed it is going to change the temperature of the system. We are keeping the same pressure. Again the energy balance what we saw in the earlier problems, H03 is equal to H02 plus energy addition. Right? It is going to increase the system enthalpy, total enthalpy. That indeed increases T03, which is greater than T02. So the total temperature increases here from T02 to T03. Now again, it is an adiabatic duct, the nozzle. If not isentropic, but still we can treat it as adiabatic duct, where I can safely say T0 is going to be constant for a steady flow. That's an assumption we are going to take. Okay. So now again T0 is constant. So now look at constant, increase, constant. So if I look at the given option, option B is correct, right? That is the correct answer. What about the other option? None of the other options which makes either T0 is decreasing or at least constant, right? Because the worst condition I can have is like, if not for adiabatic flow, I can have total temperature which is dropping, not increasing, as long as there is no moving shock. That's the very different story together. Okay, so the only option which is much more relevant over here is option B. None of the other options are even close to that. Okay. Okay then. So let us move on to the next question. It is a 2-mark question. So in a 50% reaction axial compressor stage, the local blade velocity is 300 meter per second and the axial component of velocity is 100 meter per second. If the absolute inlet flow angle alpha 1 is 45 degree, the work per unit mass done on the fluid by the stage in kilojoules per kg is. Very crystal clear question. So no need to worry on too many things here. Everything you need to calculate is given. So again, let us try to draw the turbine stage diagram. So I have a rotor. Which is rotating in this direction, say. That makes its velocity as u. Okay. So I have an absolute velocity that is coming onto the stage, denoted by C1. Its axial component is CA, with which it is making an angle alpha 1 given as 45 degree. And from the relation we can easily say C is equal to U plus W, W being relative velocity. So that means stator is already rotating, right? It is a relative to the observer. So that means for an observer, it looks like rotor is receiving a fluid with a relative velocity component W1 with an angle with respect to axial component beta 1, right? So that is how it is receiving, and rotor is leaving the fluid, or fluid leaves the rotor at relative to the rotor exit as W2. Its axial component is again CA, and it's already rotating at u, and my absolute velocity vector is going to be c2, again given by c is equal to u plus w relation. So this is alpha 2, this is beta 2. So now my velocity triangle is with us. So what are the conditions given in the problem? Alpha 2 is given, alpha 1 is given 45 degree. The blade velocity is given u 300 meter per second, and axial component of the velocity is 100 meter per second. Ca is given to you, right? So they are asking you to calculate work done by the stage on the fluid, right? So work done by the compressor stage is what? So this is what we have to calculate. And we know from Euler energy equation, work done is nothing but an energy transfer from system, surrounding to the system or on the fluid, that can be written as U times CT2 minus CT1. What is CT2? That's the tangential component of absolute velocity vector. CT1 is also tangential component of absolute velocity vector at the entry. So if I look at this diagram very carefully, I can see this is my tangential component CT1. This is my tangential component CT2. So as the fluid passes through this rotor, how much of a tangential component of velocity is changed? That quantifies as the work done. That means like rate of change of momentum. That's the meaning of that, right? So CT2 minus CT1. So now we have to calculate what is these values. What are these values? So if I just draw the entry velocity Pythagorean triplet, considering C1, alpha 1, Ca, Ct1. So I know what is alpha 1. I know what is Ca. I can calculate Ct1. So if I define the tan of alpha 1, so that is going to be Ct1 divided by Ca, or Ca is equal to Ct1 divided by tan alpha 1, and tan alpha 1 is tan 45 degree, tan 45 is 1, so Ca is Ct1. So sorry, Ct1 is Ca. So Ct1 is equal to 100 meter per second. This part is clear. U is already known. So now I have to calculate what is Ct2. What else is given in the question? Oh, this one we missed. 50% reaction stage. R is 50%. So that means R can be 0.5. So for 50% reaction stage, we know the entry and exit triangles are symmetrical. That means alpha 1 is also equal to beta 2. So that makes WT2 should be equal to CT1. That is equal to 100 meter per second. So it's an condition. So if WT2 is 100 meter per second, what is CT2? U is known. So U is equal to CT2 plus WT2. So that means WT2 is nothing but, CT2 is nothing but U minus WT2. So U is given to you 300. 300 minus 100, that is CT2 is 200 meter per second, right? So now we got all the information we need. So now I can calculate work done by the compressor as 300 times 200 minus 100. That is going to be 300 times 100. That is going to be 300 into 100, or 30 into 10 to the power of 3 joules per kg, or 30 kilojoules per kg. So now look at the options. It's option A, right? 30 kilojoules per kg. So everybody clear? Yes. Let us move on to the last problem. This is a bit interesting, and I found this problem lacks with many data. Okay, so the first data I think missing here is ambient pressure condition. That was much more important to proceed for this problem, but still we can go with the qualitative idea, okay, to answer this question. The first part I can answer from a quantification, but the second part is needs a qualitative approach. The quantification is a bit difficult here. So let us try to see this question very carefully. What is given? An aircraft which is flying at a Mach number of 1.5, where the ambient temperature is 250 Kelvin. The stagnation temperature of gases at the entry to the nozzle is 800 Kelvin. The nozzle is choked and always under expanded. Assume the molecular weight of the exhaust gases to be 29, the ratio of the specific heats to be 1.4, and the universal gas constant is 8314 joules per kilomole per Kelvin. Okay, so the keyword I have to observe here is the nozzle is always choked and it is always under expanded. It is not optimally expanded in any condition. This very important condition is always under expanded. This is a very important keyword to observe here. And the missing point, one more thing is like they did not give the unit of molecular weight. It is very, very important, but they are not given. So that's one part. And aircraft is flying at Mach number 1.5. That means it's a supersonic aircraft. But the other condition is not given, whether the nozzle is convergent or convergent divergent. That is again unclear. They should have mentioned it. Okay. So let us assume it is convergent divergent nozzle in the problem. But still, like, it's a very, very, very important assumption we have to make. Okay. So say I have an engine as with the CD nozzle. Okay. So I have an incoming flow at a Mach number of 1.5 with an ambient condition. The temperature is 250 Kelvin. Okay. So I have a nozzle entry condition given as T04. We will treat it as T04 as 800 Kelvin. And gamma is given to be 1.4. And R is not given directly, but I can calculate for the gas as the universal gas constant divided by the molecular weight of the gas. So from here I can calculate 8314 joules per kilomole Kelvin, sorry, kg per kilomole Kelvin. Is it like that? No, joules per kilomole Kelvin. So that makes molecular unit should be in 29. Again, there is one quantification factor is missing again over here. That is kg. We will see this is to be kg per kilomole. So this is the molecular weight. So if I cancel the units, so kilomole get cancels. This comes out to be 8314 by 29. That is roughly around 287 joules per kg Kelvin. Yes. So this makes the unit correct. So now what do we have from the question? The question one is such that for which one of the condition at the nozzle exit for like Mach numbers given below, the propulsive efficiency is highest. Again, they are not specified which type of engine they are using, whether the turbojet or any other type. So that is not given. but we will assume it's a supersonic flight. So it is turbojet engine. So for turbojet engine, we derived a propulsive efficiency to be 2 alpha divided by 1 plus alpha, where alpha is Ci divided by Cj. That means Ci is incoming velocity, Cj is exhaust jet velocity. So when my propulsive efficiency becomes maximum, that is the condition when alpha is 1, right? When Cj is equal to Ci, then I will have a maximum propulsive efficiency that we saw, that gives 100% propulsive efficiency. So if Cj is Ci, so first let us try to calculate Ci. Ci. So that is nothing but Mi times root of gamma or Ti. Again, assuming air standard properties, 1.5 times square root of 1.4 into 287 times, again this is missing information in the question, they should have mentioned the air properties. Ti is 250 Kelvin. Okay, so if I use this one, I should be able to get Ci as 475.408 meter per second. Okay, so this is also equal to Cj for maximum propulsive efficiency. But we are not asked to calculate Cj. We have to calculate what is Mach number. So what is Mach number at the exit plane of the nozzle? That is Cj divided by root of gamma or Te. But Te is unknown. But how can we calculate Te? Again, I am going to use the energy equation along the streamline which is passing in the nozzle. Say I have a streamline which is at state 1 to state 2 from nozzle entry to nozzle exit plane. So I can use the energy equation. T naught is equal to Te plus VE square divided by 2Cp. So from here, our is nothing but Cj. So I know what is Cj, we calculated for maximum propulsive efficiency. So from here I can calculate Te to be equal to T naught minus Cj square divided by 2Cp. And if I do that, so T naught is given 800 Kelvin, Cj we calculated 475.4. Cp, what is Cp? Cp again I can calculate from the given information using calorically perfect gas assumption, gamma R by gamma minus 1. This gives me 1005 joules per kg Kelvin. Because R is 287, gamma is given 1.4. So if I use, I will get this one. So from here I can calculate what is Te. So Te is nothing but 687.56 Kelvin. So if I use the Te over here to calculate what is the Mach number at the exit plane of the nozzle, so that gives me 475.408 divided by square root of 1.4 into 287 into temperature 687.56. So this gives me Me to be around 0.905. So now you look at the given option, none of the options are matching to this. The only closest is like 0.9 if you assume it to be around 1. So this can be taken as an answer for this particular question, but still I'm not confident to give it as an answer, but the closest one. Somehow we can quantify this. But the next question is very difficult to quantify. But we know that this condition, it is always choked and under expanded. What do we mean by under expanded? Come on, you guys studied it in your gas dynamics. What do we mean by under expanded nozzle? That means the exit plane pressure of the nozzle is going to be higher than the back pressure, right? It is not fully expanded to a condition. There is still a scope to expand, right? in this condition, what happens? You will find a expansion waves, right? Expansion fan. Because still you have to reduce the pressure. That can happen under expansion waves. So that means as long as nozzle is not under fully optimal condition, I don't get a maximum thrust. If I want to get a maximum thrust, then I have to reach towards optimum expansion condition. So if I want to go towards optimum expansion condition, or you can treat in a simple way. So thrust is nothing but mass flow rate of gas times Cj minus mass flow rate of A times Ci. Okay. So if I increase the Cj, I'm going to increase the thrust. So if I want to increase the maximum, so the thrust has to be increased. So that means Cj has to increase. If I want to increase Cj is nothing but Mach number at the exit plane times square root of gamma r Te. Right? So if I increase the Mach number, I can increase the Cj. So that means like out of this option, and I know it is always under expanded, it is not optimally expanded. Out of this one, which one is going to give you the maximum thrust? Assume none of these are optimally expanded condition, because it is given that it is under expanded always. 2.5, right? Like which Mach number is higher, that is going to give me the more higher value of Cj. So only this one will give me the maximum thrust. So this is a kind of a qualitative approach. Okay, we can't really get the number here. Thing like that closes our discussion on 2013 paper. If you guys have any question, you can pitch in. Okay, then if you guys have no other question, we can wind up this session over here. So thank you for attending. Okay, see you.